above and beyond. I'm very gratified for that some of you want to hear more, and I promise I will try and at least mostly wind up at 2:30 is the contractual hour and a half. But of course, I'm happy to keep talking if you keep asking questions. But again, don't feel ashamed about walking out. Again, the fact that you showed up is already wonderful. Okay, just to remind the crucial bits and then already add one more thing. So we define these models using the category. That I won't say again. There's a Hilbert space. We have a Hamiltonian. Here, it's a sum of local bits. These projectors I defined by drawing pictures, but then discussed how to define them as an action on that Hilbert space over there. And then there's these arbitrary coefficients. I know in principle, these coefficients could depend on space. I mentioned this morning. You could stagger them. You can do whatever you want. It still commutes with the topological defect I talked this morning. But for what I want to talk about this afternoon, I want them uniform in space. So they'll depend on this chi here, which thing is moving there, but they'll be independent of space today. I may have written down AJ this morning, but it should have been A chi, or A chi comma J. And now, but today for this afternoon, I have a picture for that. I'm just going to draw that as that. So what that really just literally means is this picture. Okay, so that's my shorthand picture. Okay, so that's the 1 minute of what I said this morning, or at least that I'm going to use. All right, so but then to do the things I want to do this afternoon, I haven't told you what it's going to be, but I have to introduce another thing. So this structure is called a fusion category, but I'm now going to add what's called braiding. And so in the following, so basically, so it just says that I now allow lines to go over each other. Before I was doing things in the plane, but now we can go over or under. And it says, again, the same idea, we can take these graphs and then evaluate them, turn them into a number. But now the rule to untwist this thing, we pick up a phase here. So this lambda ABC, sorry, omega ABC. And likewise, if we go the other way, we get the inverse phase there. And so that's how we untwist it. And this is, so then usually, you can then define things like this using that. And in fact, well, I can show you. So we use that rule I wrote down this morning, and you would then have, should have drawn it. So then this will be that, and then we can do that, and then we can use this. So that's some sum using that thing of gluing the lines together. So that's how you relate that to braiding. And this is how the Jones polynomial works. There's some subtleties I haven't told you about, but ask me about them later if you want to hear it. So you basically take your knot, you project it out onto the plane, you get these over and under crossings, and then you do these manipulations. That's really a genius thing, but now we've systematized that whole story into this beautiful structure. Okay, so right, so that's the sort of the mathy part that I'll use. But what I want to do, so the motivation now, so that's the math background. The motivation is to say something about integrability. And the basic relation of integrability is called the Yang-Baxter equation. Probably everyone's at least heard those words. But the way the Yang-Baxter traditionally has been solved is, well, originally I'll write down the equation in a second, but you just looked for solutions of this equation. And if you could find solutions to this equation, you had an integrable model. There's this whole beautiful structure Baxter came up with, and then many, many people have worked on over the decades and all that. But in this language, the picture looks like this. So this is this vertex here. But now a Yang-Baxter equation is not purely topological. It has a parameter in it. And so what now I'm going to do is I'm going to say this is function of some parameter. I mean, sorry, not P, A. A is a function of some parameter. Obviously, it's going to depend on many parameters, but I'm going to single out one particular parameter. Let me call it U. And then, so when I draw this here, so I put a U there to label the A's in this case, depend on this thing of u. So there's some formula for well, if I can find a solution. And then, make sure I get this right. So then that's some u prime, which is some value. But then the one in between depends on that. This is u prime, u plus u prime. And so the Yang-Baxter equation says, it's an equation now, in this case, for these a's as a function of u. It's a functional equation for u. So the way you would look for solutions from my point of view. So in general, you can write the Boltzmann weights of a lattice model in this fashion. Forget the category, just write it this way, and you would look for a solution. But here we now have something much, much more confined. We say, well, I'm going to define my Boltzmann weights in terms of these things, and ask, can we find an A such that this beast is satisfied? And so I guess in my convention here, we would have sort of hj of u times hj of u plus u prime. Sorry, that's hj plus 1, hj of u prime. Okay, so that's a functional, so that's a, well, so we define this using the category, but then this is a function or bunch of functional equations for the A. Okay, so that's a mess. And so Jones noticed this connection long ago between these categories. Categories didn't even really exist in that, but in the terms of not invariance. And said, well, what categories, so you have to remember to define this, we had to choose this object rho. So which categories in which row result in a solution of this equation? And he said, this is to Baxterize. So you're adding this parameter, you're adding these A's. So this is not topological. There's a sense in which, maybe I'll say a few words about it later on, which we're making things geometrical here. So we're adding more structure. It's not topological. And Jones said, well, when you can do this. And still, again, it's mostly ad hoc. A major success is you can do this systematically if you introduce quantum group algebras. And most of the categories many of the categories that we know about have something to do with quantum group algebras. And then you can be more systematic, but that doesn't cover everything. So it's still a bit ad hoc, but now we've got a lot more structure. Okay, so that's the motivation now, is to find a way, an easier way to Baxterize, to find a solution of this thing, but without, not just ad hoc and without solving this trilinear functional equation. I should say generically, take a generic category and generic object, there's just no solution. And you can pretty easily show in a given case. But what we would like, ideally, we don't have, well, I can just write down the category and you can tell very quickly, there will be a solution, what is it? Or there's no solution for a given category in a given row. And then, you can ask what row isn't simple and all these things. So that's the motivation. And hopefully, if that seems a little confusing, I'll come back to that at the end. Any question? Yeah. Well, right, so you get a solution, but not a U-dependent one. So in fact, in the old days, in the 80s, what happened is this was done before all this Jones stuff was done. And then they said, oh, wow, if we take a solution of the Yang-Baxter equation and you take some limit, like U goes to infinity in this convention, U goes to infinity, well, then it satisfies the braid group relation. So it was the logic was actually the other way around. It says we start with an integrable lattice model and we can get new not invariants. So you'll see a bunch of papers in the 80s. Yeah, well, or no, we want to find new examples where lattice models where we don't know. So I guess so in my paper, I found a few lattice models that probably are new, meaning I don't think anybody wrote them down. They're not radically different from ones that are known. But the hope so this Hagerup story that you know well. Yeah. So what I'm going to describe to you in the last 19 minutes here is at least a way to, looks like it's a simpler way to approach the problem, which makes it maybe possible to find things. Or show that the stuff we know is basically, that would be the boring, but at least useful to know. Don't waste your time looking for new stuff because it just won't work. There just isn't a solution to this thing. And so that would be useful, even if negative. No, it's a statement about these operators. So this is the little bit of the Hamiltonian. Right, so that's right. So what it would be saying, so that's right. So it is. So I guess I should have said, let me do it this way. I'll define that, a more general model. It says, so now it turns out the integrable model has to have a uniform. No, sorry, it doesn't. So this will still be integrable. So I should have said that maybe, instead of making a point to be uniform. So that model, so we're letting this depend. But from the category point of view, the U is completely irrelevant, right? It's just going along, it's just depending on these coefficients. And these coefficients don't affect any of those manipulations, that I was talking about this morning. So yeah, so okay, maybe I should have said it that way. It's an anisotropic model, we let U, and then I pick a different U for that. But notice the key thing here, the key thing, this has something to do with integrability, is the following. Notice what happens. U came first here and comes last here. And you can then, the Baxter genius stuff that lets you find things that commute with each other. And then that's why the models, it lets you construct these conserved charges. Good. Right, so, okay, again, I promised I would finish by 2:30, or at least get the key message out. And again, people can ask if they want to hear more. Yeah, actually. Right, so the idea is to find a simpler equation for A. So I want to find a linear equation for A. But then if I can solve this simpler equation, then it gives a solution, but which results in a solution of the Yang-Baxter equation. So I won't be able to prove. There's some special cases where you can prove when you do bring quantum groups into the story, but I'm going to avoid quantum groups. And so to do this, so this is was in the title of the talk, conserved currents. I want to extend what I told you about this morning to define objects that, well, I'll show, give you conserved currents for these lattice models for this Hamiltonian. And what I need to do is I terminate the defect. And so what I mean now, so remember we have these vertices. So I have this picture here. Well, now let me use a different color. So I have some defect here, and I'm just going to draw it as a squiggle line and a different color just to ease the eye. It's an object like any other one. In fact, I can call it the phi I called this morning. So I'm just squiggly line doesn't mean anything other than to distinguish this one from all the other stuff. That's all. And so again, this is our picture room. So I can define an operator I'll call J, which is this vertex here. Call that J. Let me see, make sure I used my conventions that I used. Yep. And then I can define another one, which I'll call J bar, which is just the other way around. And so this is this thing where that's phi and rho. Okay, so henceforth, and these are the H's. If I leave a line unlabeled, it's rho. If I leave an unsquiggly line unlabeled, it's rho. And if I leave a squiggly line unlabeled, it's phi. Is that okay with people? And if it gets confusing, if I forget to put a label on something, it's not that. So I define those things. And now if, for example, I can define a two-point function in the following fashion. So J bar J would just be the following thing. So that's the J bar, and that's the J, right there. And I guess times 1 over, well, there's some, no, let's just define it that way. There may be some, you might want to change the normalization, but I don't need that. Okay, and then again, you would use the rules, and I needed the braiding. That's why I needed the braiding, so this goes by all these other things. What? Yeah, so I drew it below, but you can obviously define ones that go above. But yeah, right. And actually, they're different. And in the, when I get to then yeah, you'll get to different answers. But this is just a so I say, so I define this correlator to be below, but I could then define another correlator of my notation as it were. So I do the same thing in above, and they're not the same. You can relate the two, but they're not the same. Yeah. So I use it. Yeah. Right. So this is these things, but otherwise it's there. And again, and so I should have said, oh, I should have drawn this on the board. So the point is with braiding, you can move this thing up and down without changing the value. You can't move it beneath, but I can move it above and below. So yeah. So it doesn't. So I can move those things around if you want. It doesn't matter. It's the same answer. So that uses this additional data I added this afternoon to do that. So. But the point is now, the reason why I define these J's, because this is going to let me write down a simple equation that for these J's, this linear equation I mentioned, and if you can find A's that solve this, or A's and J's that solve this, then you will, at least you'll get to do. So the equation is this. It's the analog of a divergence-free one. A divergence-free condition. Let me just write it down instead of talking. So again, I'm following this convention of unlabeled things. Sorry, this changing. And so this is not u, it's mu. It's some parameter, which I'll say a little bit more about in a sec. So go like this. This one go like this, and this one will go like that, and there's a mu missing. Okay, and this again, this is the undercrossing. There's an undercrossing here, sure. These terminate the edge. Okay, so now this looks like a divergence-free condition. And well, yeah, I'll babble a little bit more about this. But the point is, if you can find a solution to this equation, you see, so this is the dot, this is the Hamiltonian, this is, remember, this is HJ. This is my picture for HJ, that's sum over the projectors with arbitrary coefficients. And so it sort of looks like a divergence-free condition, and maybe it's even more obvious if I look at the, so if I call this, say, call this QJ, so let me call it J, capital J sub J, right there. If I then take this combination that, so this is then J sub J equals that, then you can see from this relation that the sum over J sub J commutes with H. Up to boundary stuff that I'm going to ignore. So you choose the boundary conditions, right? Because it cancels. Okay, so notice this one happens. Oh, wait. Yeah, sorry. So this one happens before that you act with the Hamiltonian, right? So this is J acting first, then you act with the Hamiltonian. This one, you act with H, and then you act with the J. Now these are different, but if you sum them up, this thing cancels telescopically, because you notice this moves down to here. And again, I'm going to ignore any boundary thing. So at least locally, that's why I call it a conserved current relation. So this looks like a divergence-free thing. And in fact, well, this occurred in various independent places in literature. About 20 years ago, Smirnov, the mathematician, Stas Smirnov, used this kind of idea to prove that the Ising lattice model is the Ising conformal field theory. And And what's remarkable for the simplified categories that I did this morning, all the ones that I used, it turns out there's a really nice, this all reduces, all these F symbols and all that other stuff I wrote down this morning reduces to one remarkably simple equation, which is, this is really cool. Good. Talk about this for a few minutes and then stop. So so I should say this does not solve the equation. It says if you can find a solution of this simpler equation, so I did not prove this for general categories, but for all the kinds of categories, if the A's satisfy this equation, whenever n, A, phi, B, well, I guess it's equal to 1, so not 0, then if you can solve all of those, then you have a solution to that, which is stunningly simple. So you get all these F symbols, but they all cancel. Unfortunately, Tobias Osborne worked out what the generalization was to more complicated categories, and it doesn't look like there's as simple of an answer. The equation makes sense, but it doesn't simplify. So then the question just simply comes, well, can we solve this? When is the solution? Well, so we have the unknowns. So we have one unknown for each, in front of each projector. Okay, and then and this is and we have mu. That's the other unknown. But then we have all these. So we have an equation anytime this is non-vanishing, and then we have these unknowns. But you see now, if we look at this graph, so we start with, so let's think of all the objects, all the chi. So these are the ones so that's the ones where n, rho, chi. I think one of my indices moved up, but it doesn't matter. So all chi with, because remember that was the expansion we did. Rho chi. Why drew it at an angle? So sorry, where's the eraser? That is. So that defines the chi. So all the chi that allow that. And so then we sum over all the chi. But then you see, so we can now make a graph. So we start out with the first chi. So chi1, the first allowed chi in there. Well, then I fuse it with, so I just draw this following picture. I fuse it with rho and I get something else. Maybe I get two things. Right. And so these are the things where so then this is, say, chi2, chi3, and so these have n, chi1, chi3 rho, phi equal to 0. And then I can keep going here. Now you may get a cycle, but what you can see, which is really cute, is if this is a tree, you have the same amount of constraints as you have degrees of freedom. So if this is a tree, so if there's not a cycle, you have a solution. So if this is a tree. There are a few cases I found with cycles, though, that do have solutions. Generically, they won't, and you can see that. But occasionally, if there's some coincidence among these phases, the braiding phases. So anyway, so sorry, I swore I'd finish at 2:30, and it's 2:30. So the moral of the story is this. The category lets you define these nice lattice models. This morning I said, okay, well, they have this nice property that they admit these topological defects. Well, now we can terminate these topological defects, and all the same rules still apply. So we can define these J's. Now, if we demand that J satisfy this equation here, that's a condition on the Boltzmann weights, right? Because a priori, the A's, the things in the Hamiltonian weights. And then we get a conserved current. Now, The reason why now you shouldn't be stunned, this doesn't prove it satisfies this much more complicated Yang-Baxter equation. You shouldn't be stunned because this is a really non-trivial conservation law. And when you have more symmetries, things are nicer, and maybe the model is integrable. In fact, there's an old thing. So what I'm about to say is just motivation. It's not directly applicable. But there's an old thing when people were doing integrable building in the 70s. An old observation, at least there's a very old paper by Shankar and Witten in the late 70s. And what they said is, well, look, in an integrable model, you have this, we know you say you conserve momentum and you conserve energy. And so forth. And okay, we know that you can have particle production, but in an integrable model, you can't have particle production. And the reason is because in a collision, you might have to conserve p cubed or p to the fourth. And what I mean by that is individually, the sum of the individual p cubes has to vanish. And that's what these extra conserved currents of integrability guarantee. But the point is you only need to do that once. You only need to say, okay, I've got energy momentum, everything satisfies that, but I only need one additional conservation law, say conserve p cubed, the sum of the p cubed of the individual particles, to make the scattering completely elastic, and that's basically an integrable model. So this is not p cubed because it's fractional spin, but at least as a motivation, if you can find a conserved current like this, then maybe it's not stunning. And in all, like I say, in all known examples, you can. So one thing, so the mathematicians that study categories, I've asked many times now, at least no one has seen anything like this in categories. They say an analog comes up in quantum groups, but those are very special examples of categories. And you can find Tambara Yamakami, if people know what that category is. You can solve all this, but that's not a quantum group. 3 minutes late. But anyway, thank you so much for coming back again. Yeah, I'm happy to answer questions as long as anybody can stand. It can be. It can be. No, in fact, in the simple examples, it was. In fact, Pasquier, again, in prehistory of categories, basically guessed integrable models. So he observed that some integral models, these Andrews-Baxter-Forrester, looked like the A graph. So it's just literally this thing on a line. That's what you get for this for SL2, by the way. So SL2 for any representation, any row in SL2, you get an integral model. But that's a known thing. Pasquier said, well, if it's A, why can't I do D or E? And the answer was he could. And there he used Temperley-Lieb to start, which is what that case did. And yeah, so no, he gets new presentations of Temperley-Lieb through that. But in general, of course, it's much more complicated. But you're right, there aren't many tree graphs you might get from a category other than those. But, yeah. In principle, you can certainly write this down. And if you can write whatever your correlation for, yeah. In fact, yeah, there's Christian's thing this morning, well, can I write Z and all that? It's like, I can write that in those models, but they won't be nice in terms of it may not be nice in terms of the category. But any operator that I can write sort of nicely in terms of this category things, then yeah, I can do it. And then I can write down, I just did it, wrote down a 2-point function, but you can do it. But then you have to worry about channels and all that, because these are non-abelian operators, they're chiral operators, so when you take them around, and then these strings running from them exactly tell you how to deal with this. Yeah, so your twist fields, I know, can be probably written in this fashion. Yeah, no, as far as I know, the usual sociological thing, the people that work on twist fields or entanglement entropy aren't the same group of people who work, except for John Carty being one exception. But John doesn't know about categories. Really didn't when I last talked to him. Yeah. Yeah, good. Thank you for asking me. Yeah, and the thing. Okay, so initially it's just, so the first thing you say, if you look at the lattice models that solve this, what you'll see is U describes an anisotropy in the model. Like, so if I'm doing a 2D classical version, I skipped that today, but everything I said, you can build transfer matrices. So U is related to the anisotropy you make. So in icing, you make JX and JY different. But without this, so maybe a little known thing, you go to the icing critical point, it's whatever the value, is it log, J is log 1 plus the square root of 2 or something. But you can change JX and JY without changing the criticality, and it makes sense because it's a conformal field theory. I should be able to rescale. But the interesting thing, so I didn't say this because I was rushing. I guess Yang-Baxter is. So if you remember, I wrote this like, I can always remember this. So I wrote these things like this. So notice this is, is perfect. So if it's a planar graph, these are the angles between the lines. So you can think of U now. So I made this obscure comment is I'm putting in geometry, but now it's for real, and it comes in the discrete homomorphicity equations, why they did this. When you're doing the lattice Cauchy-Riemann, if I bend this mu will change. So this will turn into U. So that's how you can, it's trigonometric. Mu will be like e to the U or something like that. They're probably e to the some number times U, but the point is, so what this is basically say, if you wish, metaphysical, Yang-Baxter says, oh, well, this is a planar graph, but I now let these Boltzmann weights depend on the angle. So I guess Chris's question earlier on, let the U's. So if I were doing a 2D classical lattice model, U would represent the angle between the lines on the graph. So that's what we, no, it's you, I mean, the key to Baxter's genius, Baxter, by the way, sadly died a few months ago, but the key to his genius was recognizing that parameterizing things in terms of U, even off the critical point where it is that things are behave nicely or not holomorphic, meromorphic, or at least have nice analytic properties in U. And so a lot of the trickery that he invented over the years exploits this fact. So U is this kind of magical, it looks, the way I present it, it just seems like it's just some stupid parameter, but it turns out U is, in a way, the key of the whole enterprise. Transfer matrices at different values of U, in a sense I can write this down later, commute with each other. So that was, people had struggled with integral models for a long time, and finally Baxter figured out how to, this, and that was then the key to unlock everything thousands of people have done for a half century. Yeah, you look worried, Chris? Did you say mu, not you? Oh, okay, well, mu is you, Yeah, all right, so good, yeah, I should have said that. So when you get a solution of this, you realize that there is a parameterization, a parameterization of mu such that the Boltzmann weights satisfy the Yang-Baxter the way I did it. And like I say, it's roughly mu equals some e to the some number u. It's always, in the nice categories I'm doing, the unitary category, it's just a phase. Yeah, that's why it's trigonometric, yeah. Oh, good. Yeah, thank you for asking all these questions, because, I was rushing, so I didn't say all these really important things. But that's why this is trigonometric, because this just turns out cosine over cosine. And back in the old day, they worked out all these things, and they could start guessing solutions, because you could kind of see that these models all looked the same, but they didn't have, until people invented quantum groups, at least a somewhat systematic way. But that doesn't cover, or doesn't seem to cover everything. And so I think this strips, this is morally similar to the quantum group, but it's more general and strips away a lot of the quantum group. There's all this really technical stuff about quantum groups. So the category strips all that stuff out. You don't have to talk about representations of quantum groups. You just have to talk about, and so they do these things that look complicated, and then they get this really simple answer. And people, I'm sure, asked, oh, come on, there must be another way. But I think it wasn't really till this sort of story happened, whenever that started, that there at least is a more systematic. So I haven't solved this in general. Like I say, it's nastier for nastier categories, so it's not quite clear if there'll be something as nice as this. But yeah, sorry, thank you. should have said that before. These, yes. Not what I said this morning, for sure. But when you satisfy all the known examples, that's why I said when someone asked this morning, you asked this morning, oh, what models does this cover? That's why I said, I'm pretty sure I can get any rational CFT. I certainly haven't proved this, but I would be stunned if every rational CFT can't be gotten by one of these things with suitably complicated. Yeah. In a way, neither. The point, well, I mean, you can say CFTs are ways to do categories, but I think the mathematician, you're beyond that now. You have much more fundamental ways to get at categories. But the thing is, it's not, if you start with a given CFT and do this, it's not guaranteed that the CFT that you built the category out of will be the one you started with. So for example, as far as we can tell, from categories, icing and SU2 level 2 are basic. They're the same fusion algebra, and the categories are very closely related. The only difference is in various signs or maybe phases in the F symbols and all that. And the omegas are slightly different. But as far as we can tell, the lattice models you get from those two are exactly the same. But then conversely, just because you get some lattice model, as you tune the A, you can get different CFTs. So the precise, there's no precise dictionary. You start with this, you get that. You get something like that, and it'll have similar symmetries and all that. But yeah, that's the point. The taxonomy isn't exact yet.
Different ways of reconstructing CFTs depending on boundary conditions that you start.
Yeah.
Similar way you can construct these whole different families.
Well, I think there's an issue of sectors. So one thing I didn't mention at all only briefly with the icing, we said you shift there. So you can define certain, in the category, you can define like a given lattice model using some subcategory. Meaning you pick a row, so you pick, say, spin 1 for a row. Well, obviously, you're going to get a subset. So you'll get 2 models, right? So one, say, with half, the H's, the thing I called H's are half integer spins, and another model with their integer spins. And now we can map in between them, and that we would call a duality. So then, so then you have to think of this structure of, well, really, I consider all these models at the same time, and the Hamiltonian commutes in the sense that if I do this map, the Hamiltonian of one maps to the Hamiltonian of the other. So it gives this whole big kind of web of things. And again, once the categories get complicated, you can do all sorts of things. And I think there's any systematic knowledge of what you get. So there in some papers I wrote with my then student, Louis-Zach, we worked out some nice set of examples where you're mapping around to these models, and you can, and then you learn lots of things because stuff that's obvious in one model isn't obvious in the other. You've all been fantastic. Thank you so much. Okay.